Thank you for joining us today. My name is Daryl Kuda. I'm the Southeast Regional Manager for Teledyne ISCO. Before I turn today's webinar over to Rick Dye, one of our business development managers, I'd like to take a minute to introduce you to our company. Teledyne ISCO was originally founded in 1958 in Lincoln, Nebraska, where it is still located today. Our environmental division was created in 1969, specializing in the manufacturing of rugged instruments used by environmental professionals in the water, stormwater, and wastewater markets. We are a proud leader in water market, providing the gold standard for water samplers in the fight against COVID-19. Teledyne ISCO provides some of the highest quality and most accurate open channel flow meters in the market. We take pride in our products, knowing we are part of the solution to make the world a safer and a cleaner place to live. Today, Rick is presenting on the best of both worlds, high performance and non-contact in subsurface open channel flow measurement. You will learn about the versatility of the LaserFlow and will address different applications that may meet your specific needs in this presentation. Following, I will provide a brief introduction of our cloud-based software to help you efficiently manage your data, followed by an interactive Q&A session. Thank you.
All right, well, thanks, Daryl, for that introduction. As Daryl said, my name is Rick Dye. I've been with Teledyne ISCO now for many years, so I probably talked to a lot of you over those years, but today we're going to talk, again, a very exciting topic. We will talk about LaserFlow, subsurface velocity measurement. We will also be talking about some of the new things we're doing with communications, and Daryl will cover that as he stated. So what you're going to learn today, why would you want to use a non-contact sensor? You're going to learn about the principles of operation of the LaserFlow. Again, very exciting topic. We're going to talk about the accuracy of the LaserFlow, which has been proven now time and time again. And we're going to look at some of the applications you may be needing a meter like this or a device. So we will look at low-level stuff. We'll look at where you may have slow flow, high velocity sites, surcharge flow conditions, and overflow detection. So like combined sewer overflows and things like that. So the real-time data and customizable alerts will be part of what Daryl will be covering later in the presentation. So very exciting stuff, and hopefully you'll get a lot out of this. So you have probably attended our presentations before, but so there'll be some repeat in here. But if you look at if you come to ISCO, we'd love to have you at the factory. We would take you through the ISCO Flow Lab. And this is one of the probably big advantages I think we have as a manufacturer. We can do a lot of different design work, development and improvement at this flow facility. So it's very, very useful. Why do people measure flow? Well, you probably know as well as I do why people do, but I'll just rehash some of these. I&I studies, or what they call flow surveys. I&I study is inflow and infiltration. So when it rains, we should not have water getting into our collection system. If we do, then that's a problem. Enforcement, we see a lot of that industrial pre-treatment now is becoming more and more popular. And then hydraulic modeling is obviously a big one. We want to know how to calibrate our models so we can better predict what's going to happen in our collection system when we have these events. And then billing, another big one. So water custody, water is becoming, as we all know, more precious as every day goes by. So cities that discharge to different wastewater treatment plants, and just to name some of them, you have Atlanta's, the Phoenix, Milwaukee, Boston, Denver, and the list goes on and on and on. So again, people need to be accountable for what they're discharging to the treatment plant, and they are now being billed for that. Okay, so some of the equipment options, it really comes down to how are you going to power this thing? Do you have AC power, or is it going to be battery power? You could use maybe solar power. That's another popular one. But if you look at a typical permanent application, you would see like the signature flow meter on the left normally is an AC powered device. So it's more of a permanent flow meter mounted on the wall. The one on the right is a logger style, And these are designed to be both portable or permanent. They work on a 2100 series platform, we call it. And in this case, with the laser, it's called the 2160. But these a lot of times will be in environments that could surcharge or flood the manhole. And so if you do have an environment like that, the logger style would be the way to go. The difference really is one on the left signature is going to be on or can be on all the time, taking more real-time readings. The one on the right is going to wake up, take a snapshot, and go back to sleep. All right, so just to kind of give you a quick overview of what the signature flow meter is it is what we would call a smart device. And what I mean by that is that now all of our devices are what we call TINET or smart Teledyne ISCO environmental network. So what these can do is you can basically plug in up to 9 different technology sensors, and it would scan for it and see what it is and says, oh, you're a laser, or no, I want an ultrasonic. Oh, I see you're an ultrasonic. So when you scan for it, it knows what it is, and it makes it much more plug and play. So very flexible, and again, very smart. It easily adapts to different types of communication capabilities like internet, which Daryl's going to go through with you, alarming, be able to download using a USB. We can use the standard Flowlink software. Data can be pushed to Flowlink or downloaded manually. Modbus using SCADA to a SCADA system, Ethernet, and your typical old-time analog 4 to 20 output. I should also mention we can take other inputs from different devices that may not be Teledyne devices. So with a Modbus input, we can bring that in, or an analog input. So let's talk about some of the technologies. 2150 area velocity flow module. This is the workhorse of the industry, very well respected, known out there. So a lot of you have been using these, and I'm going to go through just kind of real briefly, how does this thing work? It's using continuous wave Doppler. So it has 2 crystals in the nose, one transmits and one receives. So it's continuously transmitting and then getting the Doppler shift back. The beam angle is 20 degrees off of the horizontal, and diagnostics are also capable of that with this. Every ISCO meter that you would get or Teledyne meter you would get will have diagnostics capabilities. These are logged as a data set. So you can not only see it real time, you can log it, you can graph it, you know with confidence that your data is good, or you have problems and you need to maybe service something. We use a digital level sensor, so it's very stable. So it's microprocessor based level. So we really have no drift or very, very minimal drift with this type of sensor. We can avoid silt by even offsetting that sensor. So you can rotate it, does not have to be right on the bottom. So you can slide or turn it a little bit off to the say 5 o'clock, 7 o'clock position. No manual profiling is required. So it's taking these readings, and you don't have to go in and do any profiling. Can be installed without a confined space entry in some cases, which is the picture in the top right. You'll notice that is what we call a street level installation tool. And these work really well up to a certain point. Of course, the manhole depth will dictate a lot of that. All right, so what is area velocity flow measurements? Let's just kind of recap that a little bit. We have a sensor that's on the bottom typically. Q is our flow, is going to be equal to the area or wetted area. And the way we find that wetted area is using a level measurement technique. And one that we most commonly use for us would be a pressure sensor. We also can provide ultrasonic, and there are different ultrasonics out there for other manufacturers' technologies as well. But these are the most common types. Velocity is your, obviously the velocity measurement is using normally Doppler, and there are 2 different styles. One would be contact. In this case, we have a sensor that's again on the bottom. So it's in the flow, and then we have non-contact, which I will talk about here in a minute. And that's going to be related to the laser. Okay, pressure sensor, we know the level. We transmit a Doppler signal out the nose, measure the Doppler shift, and we can calculate the velocity. Similar, very similar to a police radar gun. All right, So now why do people want to use these? Well, obviously the one on the left is not going to give you very good readings, and I don't really care which manufacturer you're using. You're not going to get anything useful out of that. And then obviously safety is another big one. Nobody wants to get in there if they can help it. So we want to do everything we can to keep people out of harm's way. All right, let's talk about now the laser flow and the principle of operation. There's an ultrasonic sensor that's mounted in the back. It has a range of 10 feet, so it can be 10 feet away from the minimum water depth. The way we designed this, and we talked to a lot of people on other non-contacts and some of the things they liked or did not like, and one of them was condensation on the face of the ultrasonic. So what we did in the design here was put it in the back. It now reflects off of the housing of the sensor itself. So we have a virtual zero deadband. So water will go all the way up to the bottom of the laser before it would quit reading level. Once we know where that level is, this is the magic behind the laser. We actually read subsurface velocity. So there are a lot of non-contact devices out there, but almost all of them use some surface velocity technique. We're the only ones in the industry currently that can provide a subsurface velocity measurement, and that is part of our patent. Similar concept, we transmit a known frequency. In this case, it's laser light frequency. We can determine the speed and direction of that. So we can also measure both directions if we need to. Okay, this slide I kind of like because it gives you a front view, side view. And what you'll see is if you stuck your hand under a laser, you would see the size of roughly a quarter. And that would focus down in a very, very tight spot below the surface. So where it's focusing that laser is where we're getting our readings. And this is known as the point of convergence. We take 5,000 spectral velocity readings, and we do all of that in just 2 seconds. So does a lot in a very, very short amount of time. So we've made a lot of improvements on the laser since it was released in 2013. The first one took about 45 seconds. This does it all now in 2. So very, very accurate and very high tech, if you will. By comparison, a standard continuous wave sensor is going to give you about 500 readings roughly. This one's doing 5,000. All right, why are we able to read in some of the conditions I'm going to show you here in a minute? Because of the signal to noise ratio. It's really all about how good is your signal, how strong is it, what's the quality of that signal compared to the noise floor. And you'll notice on the bottom, and without getting overly complicated, the bottom scale is the speed of water and frequency. And as the water slows down, that peak will shift to the left. So what's nice about this is a really, truly a measurement of the quality of the velocity reading that you get. This is made up of a couple things: particles in the water, as well as how uniform the flow is. So if my flow is very turbulent, a lot of these return signals that make this peak may not all agree. So this peak would not be as good, but it still would give you a quality, accurate reading, provided it meets a certain criteria. And that is stored in what we call a measurement called Doppler power. And when you look at the data, you need to see a minimum of 1,000 Doppler power. All right, so let's talk about multi-point, multi-depth, or how do we set these things up? They're typically mounted at the crown of the pipe. It uses the ultrasonic, again, to know where the water is. There is in this case, we're showing you a theoretical velocity profile. The peak velocity will normally be right below the surface in the center. And so what we're able to do with the laser, we can do multiple points. So we can go left to right, up to 15 different points. Each one of those, again, is 5,000 velocity readings. So we get asked quite often, why don't I just do this all the time? And really the answer is you can. Do you have power, AC power? Is it pump flow? Do we have a rapid fluctuation in our flow conditions? So those things can all affect how you choose to do this. I normally turn them all on. I'll turn on one initially to make sure I get a good reading, and that's typically the top center. Once I verify that I'm getting a good reading, then I'll turn on all 15 and see how uniform my flow is. This does not do a complete velocity profile, so I don't want to mislead you. but it does give you a very good profile of what it sees in that flow straight. Okay, been down the road. I've done many accuracy certifications tests, and happy to announce that we're rated MCERT class 2, which is better than 4% in Europe. Our current specifications are 4% of reading, so we are the highest accuracy spec non-contact device in the industry, at least that I'm aware of. Third-party test results, we've done a lot of those. One of them is what we call, or what is called, the ITRC Irrigation Training and Research Facility in Cal Poly San Luis Obispo, California. So they did a lot of testing with that. We were 1.8%. Alden's, we went all the way to the East Coast. Alden is another highly respected flow lab. They're in Holden, Massachusetts, and they were 2.7% error. Right now, I'm going to talk about some of the applications. So we designed it for large pipes, and we just kind of define that as anything greater than 36. But we're finding we're using them in a lot more small pipe applications, and we would define that anything less than 36. So some of the applications that we deal with that are challenging would be a high velocity, low level. So steep slope pipes, low level raw velocity applications. So anything less than 1 inch. So the continuous wave Doppler sensors, as good as they are, need to be covered, obviously. And that means they need to have flow greater than 1 inch in order to read. Typical area velocity sensors, again, are going to need that 1 inch. And that's pretty standard in the industry. Slow velocity applications, anything less than a ½ foot per second. And we see this in residential collection systems as well. So a lot of applications like that, which is what you're seeing on the far right there. You can see the laser dot on the water. That water is as smooth as glass. So that's a very challenging one for anything but a laser. Wastewater effluent, where a lot of times it's going through a chlorine disinfection channel or UV channels. And that's another one where we're starting to penetrate the market a lot more because nothing else reads in those applications very well. Drinking water influent is another one. Stormwater. Stormwater is a big one for us where you have a wide fluctuation in flow. So if you're trying to measure a very small amount of water because I don't have an event yet, and then it's going to go full pipe or go very deep, then the laser is a great way to go. Irregular shaped channels. So another application for these would be channel shapes that are going to vary quite a bit. So low level, high velocity application. We need our current spec is a ½ inch for minimum depth for velocity on the laser. We can read down actually even lower than that, but our spec is a ½ inch. We can read up to 15 feet per second, which covers 99% of the applications that we deal with. So the picture on the bottom right is one that's very low level and just screaming velocity. It's really moving through there. This is a better picture of that same application. The one thing to note is you can aim the laser into the flow, but you can also aim it downstream. So we don't care what direction it's installed. The mounting bracket has 2 bolts that hold it in place. There's a nice quick handle there to unsnap it, but you can also install and remove from the surface. You don't have to be in the channel or in the flow. So here's some just kind of some data that I thought was pretty impressive. If you look at this, we have very high velocity and very low level. So that average velocity is about 13 feet per second. Slow velocity applications. Again, we see this more and more with sites like that. You'll see that as a kind of a cargo bar for a temporary mounting installation. So a lot slower applications. Again, very difficult to measure, but with our superior signal to noise ratio, we're able to do that. All right, slow velocity. So this is an application where you can see the level is about 14, roughly in the 17-inch range. Our spec's a ½ foot per second, and you'll notice we're reading much lower than that. Okay, what do we need to install this? Really only a small opening is required. So we have a little slot in the top. This happens to be the flow lab at ISCO. So you can see the beam on there. So we really don't need a big area in order to be able to read. And where this is important is an application like this, which would be industrial monitoring. So industrial monitoring, if you have a application like this where you can just cut a hole in the top of that pipe or a slot in the top, that is ideal, because then you have perfect hydraulic conditions. We're able to get the level from that, and we're able to read, again, very, very low level stuff for industrial monitoring, as well as close to full pipe. So here's another good picture, or a couple pictures for you. It really demonstrates the best of both worlds. You have low level on the left. I mean, that's just barely coming out of that pipe. And on the right, we have very, very slow flow. So we're able to read both of those types of conditions. Okay, another couple good shots here, and we're seeing more and more of these types of applications. So the one on the left, again, we are replacing a flume. A lot of applications now where flumes are being pulled out, and they're just replaced with the laser. The one on the right is measuring canal water, and you can see the laser that's reading a big area of flow over a canal. So wanted to throw this in. This is just an example of some of the accuracy data that we collected. And this was done at one of the labs, the irrigation testing and research facility. And you'll notice that we were right on compared to their standard. So an application that we're replacing, again, a lot of would be this type, which the flume is backed up due to debris. It's also could be undersized. The facility has grown, or the area of town has grown. And now the flume that was designed and installed years ago can no longer handle that amount of flow. So they're pulling that out, putting a laser in. Effluent discharge. So here's another good example of a couple different applications. Very clean water. The one on the right, though, what you'll see is a lot of entrained air in that flow. So that's a very, very challenging location. I wanted to point this out because we honestly didn't know how well it was going to work till we started looking at the data. Once we collected the data, you'll notice that I saw a lot of what appear to be dropouts. They really weren't dropouts. They weren't going all the way to zero, but I did not like that data. So when I downloaded the diagnostics, what I noticed was instead of that nice clean peak that I showed you in the earlier slide, you'll see there's a couple different peaks here. One is a very low frequency, low velocity. That would be telling you we're barely moving, and that's why we were dropping down so low. In reality, what we wanted to see was this higher velocity peak. So what we were able to do in the programming of the meter is change where we start looking for that signal. And we were able to then get the real velocity. And you'll notice here from where my line is to the right, nothing was altered on the meter. Nothing was changed at the site other than the start bin that we set in the meter. So a quick correction, and we got it working without them doing a lot of construction. All right, so a couple more applications for you. Here's one where they just cut an opening in the top. You can see that water's moving through very fast. They're using some unistrut to kind of help support it a little bit. Here's one where coming around a bend, so it's a little bit of a challenging application as well. We can use a remote ultrasonic over that if we needed to. And here was one that I was at, and this is a very, very challenging application. And this one would be difficult to measure with the initial laser because it would have tried to read the level directly below it in the drawdown, not in the pipe. So what we had to do is get a little bit creative. And what we did was develop a remote ultrasonic capability. So what that will do is that will mount now either in the pipe or it can mount straight up and down outside the pipe. But in this case, where you'd want it is up into the pipe. It is mounted on a horizontal mounting bracket. So it's going to reflect off of that mounting plate. And it's going to hit the flow or level, and now it will focus the laser in the right spot. So high velocity river applications. This is one where we tested, and it's bone dry for the most part, but when it rains, it really comes through there. And again, low flow to raging rapids during the storm events. The other thing we don't have in the flow are cables. So that's the other benefit. Anybody that has done this knows it's difficult to route cables in an application like this. The other thing is inaccurate velocity measurements due to the technology. So a continuous wave Doppler sensor does really well in most applications. But as that water level gets deeper and deeper, continuous wave technology would tend to underestimate that velocity. So again, benefits: can read slow and low flow. We can easily adapt to any high flow changes. There's nothing physically in the water, and it's accurate throughout the entire range. So what do we do when we go underwater? Apologize for the disgusting picture on the left, but wanted to give you an idea what these things are capable of handling. By the way, they can handle 6 feet of submergence for 72 hours. So they are able to handle a lot of really nasty type of events. And what we do here is we have a continuous wave sensor like a 2150, only it's a 350 sensor mounted on the bottom. We mount it upside down. So now we use the pressure sensor to read the surcharge depth. And we are able to use a continuous wave Doppler to read the velocity when the laser goes underwater. Water comes up, that air pocket in the nose seals it and keeps it from getting wet. A key thing about that is people will say, okay, it went underwater. Do I need to clean it? Well, the one on the left, you probably do. But in a lot of cases, you may not have to. And that diagnostic that I was showing you earlier would tell you if you need to go out and do anything or not. Okay, so here's some data. This is a little noisy, but the bottom of the top line is going to be the level. You can see the level in red is the ultrasonic. Once it gets submerged, the blue line is now the submerged level in that application. You'll notice that second pane, that is our velocity. And when it goes underwater, the continuous wave in blue takes over. So you can see that they really are fairly seamless considering the horrible hydraulics that they're dealing with. Once that water level comes back down, it seamlessly transitions back to the laser. Okay, so here's another application where they're doing a CSO. So they're doing some overflow detection, raw water influent, drinking water. So this is, even though it's not drinking water yet, there's plenty of stuff in there. So how many sensors do you need to put in? Totally depends on your hydraulic conditions. In this case, they decided they wanted to split that in half. And so they went ahead with 2 lasers. So they can take 2 lasers, they can put them in with a signature flow meter. They can average both of those to get their readings. All right, this is another application we're seeing more and more of, and I was actually at this site. So they're using UV disinfection, and it's very challenging to pace UV channels. And so they're finding now that the laser is able to read that because it's very slow. In this application, that water was moving about 0.2 feet per second, so far below our spec, but it actually did a very, very good job. Okay, so you can see right here, our average velocity is 0.28 feet per second. And then stormwater. So if we look at stormwater, there's a couple different ways of installing these things. In this case, what we did is we just kind of installed a C-clamp setup to just temporarily monitor that. But you can mount it up into the pipe, and the one on the right, the laser is actually up inside that pipe and at the top. So it's able to kind of be hidden away from people that might want to do some theft or something like that. We also have a LaserFlow EX, which meets the Zone 0 Class 1 Division 1 rating. So very, very excited about that. There's really nothing quite like that in the industry. And we found that based on a lot of customer interest and talked to a lot of people out there that said we need to do that. So again, hazardous rating is technically required for every sewer manhole in there. Consultants we're finding are more likely now to specify Class 1 Division 1. And why not? Why not play it safe and do the right thing to begin with? We've done a lot of third-party testing to make sure that this new system did not deviate from the accuracy, and we found that no, it did not. It meets a lot of international ratings as well. And really, the EX is the only product that can provide this kind of superior performance as a non-contact design. All right, with that, I'm going to turn it over to Daryl.
Thanks, Rick. So Rick has shown you a lot of great ways and different applications that we can use the non-contact and the in-pipe AB sensors to read velocity. Now that you've actually recorded the data, how are you planning on accessing the data? So you can either retrieve the data directly by going out to the site and directly connecting to it and downloading it. You can add modems so you can call up the sites and pull the data out of it, or you can use it to automatically push the data to a server, or you can use like the analog output if it's more of a permanent application to send it off to your SCADA system, or even use the Modbus. But now we even have a better way for you to get your data. We've come out with a cloud-based software called Flowlink Cipher. And so what this allows you to do is easily look at all your data on a dashboard view. And so with this, you can quickly glance at the dashboard to see the health of your system, to see which sites are pushing, how your data looks, which then allows us to provide quick analysis of your data. You can customize your graphs to however you want, to look at your level of velocity and flow, or maybe you're only concerned with flow rate, but it's entirely up to you how you'd like to customize the dashboard. One of the other benefits is that your server is no longer on your premises. It's an Amazon web-based server, and so it reduces your hacking risk. So we've all heard of some of the larger places that have been hacked by malware. So this is no longer an issue since we have it on a protected Amazon server. And one of the best things is that we have data anytime, anywhere. So as long as you have internet access, you can pull out your laptop or tablet to take a look at your data to quickly check the health of your system to make sure everything is still up and running. And last, with the automatic updates. So the great thing about this is that you no longer have to get your IT department involved with manually loading updates. Since this is cloud-based, any improvements, enhancements, or updates will automatically be done in the background to always give you the most up-to-date software. Now let's take a quick look at our dashboard. This is the Flowlink Cipher, and as you can see, you can customize it however you want with the graphs that are showing this level and flow rate, or if you prefer scatter plots. We've added some new gadgets over on the top right, which show the battery voltage. So if you have a lot of portable meters out there, you can quickly take a look at the voltage of all your sites to easily identify which sites you need to send technicians out to. And you can see on the bottom left, we're able to create I&I charts to easily see what your infiltration is. And other things that we've added, you can see with the two on the bottom right, is our alarm gadgets. And what this is that you can set an alarm for either like low batteries or high flow, anything you want, and you can easily identify that the site's in an alarm condition by having the red outline. And then we've added the alarm gadget, which on the bottom right, that shows all your sites that are in the alarm condition. The other thing you'll notice with this software is our site screen, which we have a map view. Shows your sites. If you open up the map, it'll show all your sites. They have color-coded pins on there to tell you the condition of your site. If everything is good, you'll see it's going to be in blue or green. And if it's in alarm condition, it'll change to red. We've added attachments, which is great for when the crews go out to sites, set it up, they can take a picture of it, send that picture into the Cipher program so everyone has access to see what's going on with that site. And then we can add some other general information as far as your site information and location. So with that, Rick is going to finish up with our summary here.
Thanks, Daryl. That was a good overview of Cipher. And just to let you know, we've done a lot of these webinars with Cipher. We'd be happy to do direct ones with you if you needed to. We have Daryl, Dennis McGinnis, and myself that would be more than happy to spend an hour with you remotely and be able to go through Cipher in a lot more detail. But great overview, Daryl. All right, so in summary, let's go ahead and wrap this up. LaserFlow, it's really one of the most versatile open channel flow meters that I've ever been involved with. It's the only non-contact device that truly reads below the surface. Again, that's very, very important when you're looking at accurate flow non-contact. minimal maintenance. That's the whole game here. We don't want to be in there. We want accurate data. We don't want anybody in that flow if we can help it. And with all the different types of technologies that we have a very flexible platform. You're going to see some exciting stuff down the road. And we can, again, hook up to signature, which gives us, the ultimate in flexibility, but you'll see some other stuff. And Flowlink Cipher, cloud-based data hosting. Again, another very, very exciting step. So now we're giving you great data. Nobody's in the flow. Communications have evolved, and now you can get it off the cloud. So very excited. And with that, we'll go ahead and open it up for questions. Again, my name is Rick Dye, and you can contact me anytime at rick.dey@teledyne.com. And Daryl's would be daryl.kuta, Kuta, @teledyne.com. So with that, we'll go ahead and open up for questions. Do I need to clean my sensor if it goes underwater? And that's one we hear a lot of. And really the beauty of the laser is it will tell you really if you need to or not. So it measures the XY axis, so the pitch and roll of the sensor. So it'll know if it shifted in the mount or if something happened. But also there's a reading called Doppler power. Again, I kind of went over, which is how good the signal coming back is. And then it also has what's called sense voltage, which is how much reflected light, if the window were coated, would tell you that. So if you look at those look good, and we have good Doppler power, leave it alone. So, but good question. Yeah, so just don't immediately go in and pull it and clean it.
Right. Thanks, Rick. Yeah, we got a lot of good questions coming in. One of the first questions that came in earlier was in regards to the flow conversions. And so with all the ISCO equipment, we actually have 82 pre-built flow conversion options, but specifically for area velocity, we have a drop-down list, and so we can choose the common shapes: the round pipe, rectangular, trapezoidal, elliptical. And so you just have to tell it the shape and the size, and we can use that to calculate the wetted area. Now, if it's a odd shaped pipe, we do have the ability to use level to area data points. So we can put up to 50 data points in. So if you have a custom sized channel that you want to use.
Okay. Are there difficult applications recommended against installing the laser? Yes, there would be. It kind of depends on really, obviously, what your application is. But if you have very turbulent flow where the surface is really turbulent, then it would have a difficult time of measuring the level, and then it couldn't focus really the laser very well. So need to look at those applications. I don't know what would, to be honest, what would work better, but we would see it in the diagnostic of the level, the ultrasonic level. We would notice that in the signal strength, and we would notice it in the velocity. So run it by us, make sure we give it a kind of a look through and go, well, maybe it'll work, maybe it won't, but we'll tell you definitely what you could expect on that. So it's not going to work everywhere, but it'll work in a lot of places. So.
Right. The next question kind of goes in line with that one. They're asking, do we need a certain amount of straight pipe prior to the measuring point? Where the key is that you're looking for uniform flow, kind of like with that previous question. So with the ISCO sensors or any sensor trying to calculate accurate flow, you need uniform flow. So there isn't a specific number of diameters upstream that you need, because depending on how fast the velocity is going to really kind of determine how much straight run you need in front of the sensor. The rule of thumb has always been 5 upstream, 2 downstream, but with slower velocity, the flow stabilizes and is more uniform than if it was a higher velocity.
Right. Good point. what I typically tell people is it's going to read roughly a loaf of bread in the flow, depending how high up it is. So if your loaf of bread is representative of what your flow channel is, then you're good. But yeah, there's no real 5 up, 2 down kind of thing, as Daryl mentioned. So just kind of look at it and give it a fair shot. But it's wherever the laser is going to read the velocity is going to be extremely accurate. Does that represent your channel? That's up to you on that. Variable rate data. So I had a question on that. And that is one that we've been doing for years. A lot of people don't even know about it. But all of our equipment has the ability to manually or automatically adjust how often it takes readings based on something happening. So if I know I'm normally 8 inches deep or in that range, but if I go to 10 and I want to, something's happening, I want to take more readings, all of our equipment can do that. So it can automatically adjust data read, data storage, as well as the data push. So maybe I just want to push to Flowlink Cipher every 12 hours, every 24. But if I have an event, I want an alarm sent to me. I want that data coming to me every 5 minutes as fast as you can send it to me. And I want to be able to see that. Then you can do that with Flowlink Cipher. You can do that with any of the meters that we have. So very important feature and something you need to keep in mind if you're doing stuff like that with maybe stormwater or CSO, SSO monitoring data. So good question.
All right, I'll take these next two. They're kind of in the same line. The question is, what is the maximum velocity that can be measured? It's 15 foot per second is our maximum velocity. And so earlier we did have a question asking about what the minimum range is. So our published specification is a 1/2 inch of water depth and a 1/2 foot per second for the minimum velocity. But we have measured and used the laser in applications that have had slower velocity. As Rick had shown earlier, we're measuring all the way down to a 1/2 foot per second. But on the high end, yeah, we've have actual data for applications that have been in the 8 to 10 foot per second range. So yeah, it's pretty fast. And using a non-contact sensor is actually fantastic for those really high velocity applications. Now, the other question that came in is, can the LaserFlow handle levels of 0, specifically within a stormwater application? Yeah, it can handle 0. It has a ultrasonic sensor, and it doesn't, so it's non-contact, doesn't have to be wetted. It'll just read off the bottom of your channel if you calibrate that to 0. One thing you do want to be careful of is that if it's in direct sunlight, put a sunshade over the top of it, because ultrasonic sensors use temperature to calibrate the speed of sound. If it's in direct sunlight, that could actually have an effect on the temperature of the sensor, which would then, kind of mimic a drift. But nope, stormwater application's perfect for it. And then along with what Rick said, you can actually program it to, start reading level, velocity and flow when the level gets so high, so you can have a 0 level cutoff, and then you can have a variable rate data storage for when the storm event happens.
Good points. Good points. Pipe sizes, accuracy. Hear that a lot as well. It's okay. I have a big pipe. I have a small pipe. Really, we need about an opening of maybe 3 to 4 inches wide, about a foot long, like I showed in the slide, to read. So we can read in really 4-inch, 6-inch pipes. 4 might be pushing it, but we can go reliably 6-inch all the way up to you name it, rivers, blah, blah, blah. So we don't care, but what you need to be aware of, again, is what that thing is going to tell you is what it sees. So if you have good hydraulics in a river, then great. You have a loaf of bread in a river that's going to tell you very accurately what it sees. In small pipes, then yes, we're going to very accurately tell you what it sees, where it sees it. So not so much the pipe size, it's more of the maximum distance is going to be 10 feet from the minimum water level.
All right. Next question came in was, is there a way to detect backflow or reverse flow in an open channel? Yes, the LaserFlow sensor can read forward or reverse flow. By default, it's set to read the positive velocity, and you just have to enable the option to have it scan and search for both positive and reverse flow. Same goes for our our in-pipe AV sensors at 2150. That will automatically detect reverse flow. Essentially, it's a Doppler shift, and so it just recognizes which direction based off of the Doppler shift. And I'll take the next one too, Rick. It's says, is the laser flow, let's see, will the laser flow be affected by solar radiation? That I do not have an answer for you. We do have a sunshade that would go over the top of it, so I'm hoping that would block it, but I do not know if any tests have been done specifically for solar radiation.
Yeah, I would say I don't know of any problem with the laser, but it would be the ultrasonic, and it would be temperature related. So I don't think light would have any problem with the laser beam itself, but temperature would certainly affect the ultrasonic, which would affect where it's focusing and the distance and stuff like that, but nothing that I know of on the laser. All right. So I have a question on DuraTracker. Somebody spotted that in the video or one of the pictures. So yes, we have a new meter coming out, not here yet, close, called DuraTracker. DuraTracker, you're going to see a whole new presentation on that, but that is our new, eventually replacement 2150. That will have Bluetooth capability, so you can download it. It will have all smart sensor technology, so laser, whatever you want to hook up to. I'm not going to spoil the whole show for the next one, but yes, some of you have noticed that thing in one of the pictures in the presentation. We did show that at the WEF collection event just recently in Detroit. So very excited about that. We are moving full speed ahead on our new flow technology. So that will be available. We will do a whole new webinar on that, and you will see it shortly. So look forward to that.
All right. Somebody else also noticed that they want to know what the difference is between the black and blue laser flow sensors. Great question. The blue ones are for the non-hazardous locations, and then the black sensors are EX or intrinsic safe rated sensors. They connect through a IS barrier, and then they can be interfaced with our signature or the 2160 modules. And then the DuraTracker that Rick just mentioned, we will also be able to connect the blue lasers to the DuraTracker, and we will have an intrinsic safe DuraTracker that the laser flow sensor will connect directly into.
Yeah, I think what's important about that is we will now have a intrinsic safe modem that could be in the manhole. So everything intrinsic safe can be in the manhole, and get your data out to Cipher, and away you go. So yeah, I think that's going to be very, very important. We have anything else?
Yeah, we actually got another one came in. Somebody's asking about the advanced velocity settings versus flow conditions. Do we have any rule of thumb? So the advanced programming, what I've found is that most applications do not require you to go in and use the advanced programming settings. Most applications, you just tell it your pipe size, calibrate your level, and you're done. So the advanced programs are for, if we're trying to do, like if we need to turn on the adaptive focus option because the hydraulics has like a the hydraulics aren't perfect. Like, so there's a little bit of a hydraulic jump in the flow stream where the level is a little bit lower under the sensor versus where it's reading velocity. We have the adaptive focus option to overcome less than perfect flows. But I guess the rule on using the advanced options is if you're having problems with it, download the data and contact Rick or I to have a look at it, and we will help you identify if any advanced options need to be done.
Let's see, one is, does fog, heavy snow, and rain prevent laser measurement? Theoretically, I guess, yes, it could, depending on how much rain you have. We do have one that is one that I did from Minnesota, and it was frosted over, cold, obviously winter, and it read really just fine. So it should be able to handle that. Depends on, again, what the conditions are, but as long as it is powered up and can warm that glass, that window, you're good to go. So really should not matter during normal operation. And then I have another one from an anonymous attendee. Can McManus lay down some serious riffs on this so we could, Steve McManus is a heck of a guitar player, but I don't think he's on the call. So he won't be able to play today, but we could set that up as well. But anyway, I think we're probably done for the questions. Thank you all for attending. Really appreciate it. Laser is doing great. And we have new, again, electronics with the Dura tracker coming out shortly, and that should be released 1st of July, just so you know. And that's going to be able to handle all kinds of different technologies, and moving forward, that is where we're going. So appreciate it. Daryl, do you have anything else to add, or are we going to shut her down?
Yeah, I think we're about out of time on this now. So if you do have additional questions, Sharon will provide you with some information to email us, and we would be happy to get back to you. Thanks.
Thank you all for attending.